sort of way for you to pick up on this. So where we're starting right now is with implicit differentiation. And if you're wondering, this material is in section 3.5 of the textbook. In particular, implicit differentiation is a topic that is very much going to play a role in the Calc Lab that y'all are working on right now. Take a look at Canvas to see when the Calc Lab is due. But for this particular topic, I want a sort of an introductory example here, and I want to look at two different curves. So this curve is what we call an explicit curve. Explicit means that y is a function of x. So if you can write something in the form y equal a function of x, it's termed explicit. Similarly, a curve of this type is called implicit because no matter how hard I try, I cannot write this in the form y equal, say, a function g of x. It just won't happen. In fact, this function, if you solve for y, you end up getting that y is the square root of 1 minus x squared, so long as y is greater than 0, and you get minus the square root of 1 minus x squared when y is less than 0. And when y is equal to 0, you just get the 2 points. You get plus or minus 1 for your points. But I'm not going to list those. The point is, this picture is nothing more than the following. It is a circle of radius 1. So it's a circle of radius 1 that is centered at the origin. So the curve on our left here, this curve, is the upper half of that circle. So this is the curve y equals square root 1 minus x squared, and then the implicit function x squared plus y squared equal 1 is the entire circle. And the question that I want to ask this morning is, should these functions, one of them's a function, one of them's a curve, but should these two objects, should these two curves have the same derivative? You might think about whether the answer is yes or no here. If I'm just comparing top to top, the answer is probably yeah. But if I'm comparing the whole curve, maybe the answer is a little bit different. So I want to take a look at this. We'll start by checking on the derivative of the square root function here. So if we take the derivative of this curve, you know the derivative of a square root is 1 over 2 times the square root. But then because of chain rule, you have to multiply by the inner derivative. The inner derivative here is negative 2x. And you see here that the negative, or that the 2's cancel, which leaves you with negative x over the square root of 1 minus x squared. So that's the derivative that we have for the upper half of the circle. This would give the slope of the tangent line anywhere along the upper half of that circle. Similarly, suppose I wanted to check this versus the derivative with respect to x of x squared plus y squared equal 1. Now, we haven't really differentiated anything like this before. The main difference here is that you're going to treat y as though it's some unknown function of x. But rather than write f of x squared in the problem, I'm just going to keep y and understand that anytime I differentiate a y term, I have to multiply by y prime. I have to multiply by that function's derivative because of chain rule. So distributing the derivative across, we've got the derivative of x squared, which is 2x, plus the derivative of y squared, which is 2y, but times the inner derivative, which is y prime. Technically, I would have done that over here as well with the x. When I differentiated it, I could have had 2x times the derivative of x, but the derivative of x prime is just 1, so that's why it's not really showing up over here. I could write times 1, but we don't ever really do that because it doesn't show up. But y is a different story. Since y is some function of x, then we just treat it implicitly as when we take the derivative, acting like it's just an x value, but then you have to multiply by the inner derivative, which is y prime in this case. And then finally, if you take, so we're distributing to each piece here, finally, if you take the derivative of 1, the derivative of 1 is 0. So I want to solve this for y prime. So if I solve for y prime, I get 2y times y prime is negative 2x. And so y prime is negative 2x divided by 2y. You see here that the 2's cancel, so this is negative x over y. And this is not a great answer. We found y prime here, but it doesn't match our answer above, or does it? If you look here, these two things hopefully would be the same, but do they match or not? Well, they do and they don't. It depends on where we are on the circle. So if you go back up here where I defined it, if y is greater than 0, we can replace y with this. Because this is what y equals. Y equals either this if you're on the top, or this if you're on the bottom of that circle. So if we're on the top of the circle, then we can replace y with the square root of 1 minus x squared. So that's the derivative from the top. Or if we're on the bottom, then this derivative would be given by this value if we were on the bottom of the circle. In other words, y greater than 0 here, y less than 0 here. So we've got two different derivative formulas depending on whether we're on the top half of the circle or the bottom half of the circle. But what I want you to see is we do in fact get the exact same answer if we're talking about the exact same part of the circle. So this is for the top half of the circle, and notice it matches the answer we got here for the top half doing the problem implicitly. So this method that we're going to be looking at is a way of figuring out derivatives on any sort of curve, not just a function. You're doing a little bit of this in the calc lab with these parametric curves, but we're going to do implicit differentiation here in this lecture. And this lecture might be kind of long, so as we're going through this, if you run into any issues, just simply pause it, come back to it. I don't expect you to sit there for the full time. It's probably going to be close to an hour long. I don't expect you to sit there for that long. But you can pause it and return to it at your convenience. All right, so let's go on to a first example. The main thing I need you to be able to do at this point is implicitly find the derivative. This is what will be tested in the quiz on Friday, along with something that we'll talk about in Wednesday's class. So if we assume that y is a function of x, find dy dx for this curve. So the main way that you're going to do these is you're going to take the derivative of the curve. So the derivative of this curve is, remember, it distributes all the way across, even across the equal sign. So the derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared times the inner derivative y prime. And the derivative of 4 is just 0. So this looks an awful lot like the problem we just did. If you solve for y prime is equal to, let's see, negative 3x squared, and then we're going to divide by 3y squared, which is negative x squared over y squared. Now, here's the difference between this and the last problem. If you go back to the last problem, we knew a formula for y. In other words, we knew how to solve for y, which means the derivative that we ended up getting was explicit. It was a function in terms of x only. But if you notice here, I'm probably going to have a difficult time solving for y because unlike the previous example, this is y cubed, and I need to solve this expression for y to be able to determine what y squared is. So unfortunately, this is the best we're going to do. The best we're going to be able to do is say that the answer is negative x squared over y squared, and this is an implicit derivative. It's not, the derivative isn't just in terms of x or just in terms of y, it's in terms of both, which means at each point along the curve, you have to evaluate the x and y coordinate at that point to tell me what the derivative is. For example, if we were, say, at the point 1, 2, then the derivative of this curve, which remember is slope, at 1, 2 would be negative 1 squared over 2 squared, which is negative 1/4. We need to check, I just came up with this off the top of my head, but we would need to check that 1, 2 is actually on the curve. It probably isn't, since I just pulled it out of thin air, but we would check that that point is actually on the curve x cubed plus y cubed equal 4. And I don't think it is, because if you plug in x equal to 1 and y equal to 2, you get 9, which doesn't equal 4. So 1, 2 isn't actually a point on the curve here, but if we were to try to evaluate a point on the curve, this is how we would do it. All right, so let's do another example. We're going to find the derivative of this function implicitly. So I'm going to take the derivative of x minus y quantity squared equal x plus y minus 1. We're going to distribute to every piece, so I'm going to take the derivative of the left-hand side and set that equal to the derivative of the right-hand side. Now, on the left-hand side, we have something squared, so we know the derivative of that is 2 times that thing. But then I have to multiply by the derivative of the inside. And on the right-hand side, the derivative of x is 1, the derivative of y is y prime, and the derivative of negative 1 is 0, since the derivative of a constant is 0. Okay, so we've got 2 times x minus y. All right, the derivative of x here is 1. The derivative of y is y prime. And so we've completely finished taking the derivative at this point. Now, to complete our answer, we need to do a little bit of algebra here. And the algebra is going to be a little bit tricky, but we need to solve for y prime. It's not enough just to do the differentiation. You have to then solve for y prime so you know what the formula for the derivative is, whether it's implicit or explicit. All right, so that's going to require me, unfortunately, to FOIL this out. So I'm going to FOIL these two terms. So I'm going to get x minus x times y prime minus y plus y times y prime. And then I want to collect terms, so I'm going to collect all my y primes. So let's see, we've got 2x minus 2x y prime minus 2y plus 2y y prime. If I collect all the y primes, let's see, I'm going to take all the y primes over here on the left-hand side. So we've got minus 2x from this term, plus 2y from this term, minus y, minus, if I bring this one over, that's a minus 1. So all of those are times y prime. And then bring everything else over to the right. I've got a 2x here, which would be negative 2x when I subtract it over. I've got a minus 2y here, which would be plus 2y. And I've got the 1, which was already over here. So y prime then would be negative 2x plus 2y plus 1 divided by negative 2x plus 2y minus 1. And you might be pretty excited there thinking they cancel, but unfortunately they don't. So the best I can do is just leave it as is. dy dx is negative 2x plus 2y plus 1 over negative 2x plus 2y minus 1. So this is our implicit derivative formula. We don't really have a good way of solving for y in this problem. If you look, because of the y squared term here and the y here, I'm not going to be able to solve for y explicitly, so this is the best we can do. You're going to want to do some simplification on these problems, but you don't want to let the algebra get out of hand. But ultimately, we do want to solve for dy dx, or y prime. All right, let's take a look at another example. So for this particular example, we're looking at this term right here, which you should be very careful with, this term right here as well. Both of these terms require product rule. So these are going to require product rule. because you have two functions of x multiplied together. You've got x squared times y cubed, but y, remember, is some function of x. So this is why its product rule is you've got two functions of x that are multiplied together. So rather than do product rule twice, because I'd have to do it for the first term here, and I'd also have to do it for the second term here. So rather than do product rule twice, instead what I'm going to do is a little bit of algebra. So I'm going to say, let's say y is equal to, I'm going to pull out, let's say y squared. And then we would have x squared y plus x cubed. That way I'd only have to do product rule once. Okay, so if I take the derivative of both sides, then over here the derivative of y is just y prime. That's fairly straightforward. On the right hand side I have a product rule set up, so I'm going to treat this as my u, I'm going to treat this as my v, and I'm going to come over to the side here and say, okay, well, u is y squared, so u prime is 2y, y prime. Be very careful about that. Anytime you take the derivative of a y term here, you have to multiply by y prime because y is a function of x. Similarly, if you look at v, if v is x squared y plus x cubed, then the derivative of that is, well, I've got a little bit of a product rule here. I've got 2xy plus x squared y prime. Notice this is product rule. So I couldn't really get away from doing product rule twice, but this is how I'm going to handle it. And then the derivative of x cubed, don't forget that, is 3x squared. All right, if I put all of that together, then I've got u prime times v plus u times v prime. And I'll just be honest with you here, this is a pretty messy problem. It's not a problem that I would give you on a quiz or an exam because the algebra here is just, honestly, it's just kind of bad. But you could solve for y prime here by stretching out all these terms, but I'm just going to leave it like this. You know, you probably shouldn't. You should probably factor out a y prime, collect the y prime term, solve for y prime, but I think we're just going to leave it like this. What I did want you to see with this example, though, is anytime you have a function of x multiplied by y, you must do product rule on those terms. All right, let's do another one. So here, if you're looking, you should notice, oh, there's an x times a y. I'm going to have to do product rule. So if you take the derivative of both sides, so we'll start with the left-hand side here. The derivative of e to anything is e to that thing, but then I've got to multiply by the derivative of the inside. The derivative of e to the 4x is 4e to the 4x. Remember, the derivative of e to the ax is ae to the ax. That's a formula from previous in the class. And then minus, here we have 5e to the 5y, but rather than multiplying by the derivative of 4x, which is 4, you multiply by the derivative of 5y, which is 5y prime. So don't forget the y prime on that term. Okay, I've still got to go over here and do product rule. So the derivative of x is 1 times y plus x times the derivative of y is y prime. And then on the right-hand side, we've already taken all the derivatives there, so this is what we have. Okay, if I wanted to solve for y prime, I can distribute this e to the xy term. Then I can combine all the like terms. So I'm going to take this and add it over. I'm going to add it over to this side, in which case I'll get 5y prime e to the 5y plus the existing x y prime e to the xy. And then I'm going to bring all the other terms over that don't have y prime. So this term, for example, doesn't have a y prime, so I'm going to bring it over and subtract it. So this will be 4e to the 4x minus y e to the xy. Okay, both these terms have a y prime, so I will factor it out. And then finally, solve for y prime by dividing this term over. And so this is the derivative of that given implicit curve. Once again, it's an implicit derivative here because I have both x and y in the formula for the derivative, but unlike the previous example, I was actually able to pretty easily solve for y prime here. So just taking a look back through these examples, the biggest hurdle is understanding chain rule, which we did right before break. You need to go back and review chain rule and hopefully understand how chain rule works at this point. And algebra. Those are the two biggest hurdles here. The basic derivative formulas are the same. So there's a couple examples here of finding derivatives implicitly. What I would like to do now is look at a problem that involves finding points of tangency. So I have a curve here that I want to calculate the implicit derivative of. And I want to look at what points that curve has horizontal slopes and at what point that curve has vertical slopes. But first I want to talk about what horizontal slopes and vertical slopes mean. Horizontal slope in this context means that when I find the derivative will be 0 anywhere we have a horizontal slope. So these are at points x, y where the derivative is 0. Those are points at which the curve has a horizontal slope. Points at which the curve has a vertical slope are places where the derivative becomes infinite. So the derivative is either plus or minus infinity at whatever points x, y that we end up finding. Okay, in case you're wondering what this curve looks like, let's hop over into Desmos real quick. So in Desmos, here is the curve that we are currently calculating. And if you want to enter implicit curves into Desmos, you just enter them exactly as they show up. So here's the curve that we're differentiating. It is the curve for infinity. Notice you can see we've got vertical slopes over here at 2 and -2. We'll show that. And then we've got horizontal slopes here, 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 and here. So let's see if we can figure out exactly at what points those take place, then add them to this graph so we can see that we're doing this correctly. All right. So we'll start by differentiating this curve. We're going to take the derivative of both sides. On the left-hand side, we've got 2 times all of this times the derivative of the inner function. On the right-hand side, we've got 4 times the derivative of x squared is 2x. The derivative of y squared is 2y, y prime. Okay, finish taking all the derivatives before you do any algebra. The derivative of x squared is 2x. The derivative of y squared is 2y. y prime. All right, I need to solve for y prime here. So I'm going to, unfortunately, have to FOIL everything out here to figure out the y prime terms. So we'll start with 2x squared times 2x. You get the 2 and the 2, so that's 4x cubed plus 4x squared y prime. And then the y squared term will distribute. So you're going to get 4xy squared plus 4y cubed times y prime. So FOIL out. If we FOIL out these terms, that's what we'll get. And on the right-hand side, we'll distribute the 4. So you're going to get 4 times 2x is 8x. 4 times negative 2 is negative 8y prime. Okay, we're going to collect all the y primes on the left. So every term that has a y prime, you've got this term, and this term is going to get added over. So it's going to be a plus 8y. All of those terms have y primes. And then this term will both get subtracted over, along with 8x, which is already over there, giving us this. So y prime is equal to, you've got 8x minus 4x cubed minus 4xy squared divided by this. So there's my derivative. It's not particularly beautiful. It is kind of difficult to sort through there, but I'm only interested in points where the derivative has horizontal slopes or vertical slopes. So let's start with horizontal. So you get horizontal tangents if and only if the derivative is 0, which this derivative is 0 if and only if the numerator is 0. So at any place where this thing is 0, you will end up getting horizontal tangent lines. So every term here has an x. I could factor that out. We know that from looking at the problem, we know that those tangents occur for both positive y and negative y. So how about I just solve this for y squared? So let's see here. I've got negative 4x y squared equals negative 8x plus 4x cubed. If I then divide by negative 4x, negative 8x divided by negative 4x is 2. And then negative 4x over here would be negative x squared. So y squared is equal to 2 minus x squared. Okay, so I get horizontal tangents anywhere that y squared is equal to 2 minus x squared. All right, well, let's go back to Desmos really quick here. So if you look at these points, I've got a point here on the curve where it looks like I'm horizontal, and a point here on the curve where it looks like I'm horizontal. So both of these have horizontal slopes. And then over here I've got my vertical slopes. Okay? So how could we determine where these points occur? All right. Unfortunately, this is not the easiest thing in the world. To determine where those points occur requires me to go back to the function itself. So here's the function. If I take that function and write it down over here, I will have, let's see here. I will have x squared plus y squared squared equals 4x squared minus y squared. And what you see is I could replace in this formula, y squared is equal to this when the slope is 0. So I could replace everywhere there's a y squared, I could replace it with 2 minus x squared in this formula. And then I would have something that's in terms of just x. I could then solve this for x, and then I could plug that back into here, and that would give me the y value. That's actually kind of a lot of work to do that, but do you notice that there are going to be 4 solutions to this? There's going to be 2 solutions for each x value and 2 solutions for each y value, which means there's going to be a total of 4 points where the tangent line is horizontal. The same thing is true for the vertical slopes. If you wanted to find the vertical slopes, you would just take this, set it equal to 0 to be able to find the points where this is vertical. So vertical tangents occur anywhere 4x squared y plus 4y plus 8y equals 0. And that's going to be much easier to solve because the y term pulls out. 4x squared y plus 4y cubed, right? Yeah, sorry, I had a little mistake there. That should have been a 4y cubed. So pulling out the y, we'd have 4y squared there. And then we would have 8 there, y equal to 0. So here you would have, when y is 0, you could plug that in over here and get 4x squared plus 8, right? When y is 0, that's what you get over here. So 4x squared plus 8 equals 0. You would get x squared is equal to negative 2. Oh, whoops, made a mistake. Let me go back real quick. So yeah, actually I'm going to have to do this one just like I did the other one, where I would have to solve for this thing in terms of x squared, it looks like. Yeah, so my apologies. So I would take and solve. I'd have 4x squared equals minus 4y cubed minus 8y. And so x squared would be negative y cubed negative 2y. So I could take this x squared, plug it in for everywhere I see an x squared in this problem, and use that to solve for y, and do it just like I would do the horizontal tangent. Now this is a very challenging problem. I did want to talk about this problem with you though, because I wanted you to see generally how this is done. We're going to do some much simpler examples coming up here in a second. But I wanted you to see with this example that there is the possibility to have multiple tangent lines of a single value on the curve. Here we've got 2 vertical tangents. We have 4 horizontal tangents. All right, let's look at some simpler tangent line problems. These turn out to be the easiest problems for us to do. So here are the steps for doing what I just did, except we're looking at the tangent line in a single point rather than trying to find where all of the tangent lines are vertical or all the tangent lines are horizontal. So suppose we have this curve, and I would like to know what is the tangent line at negative 1, 1. Okay, Let's go back over to Desmos real quick. So we've got, instead of this infinity sign, we've got x squared minus y to the fourth equals x cubed plus y to the fifth. And notice how you've got this sort of, it's trying to draw it in, but it's not doing a really good job. Sometimes that can happen with implicit curves. They're kind of hard for graphing utilities to graph well. So let's see, I'm interested in the point negative 1, 1. So we're interested right here. Our objective in this problem is to find the slope at this point. So what is the slope along the curve at this point? All right, and the way that you do this is following these steps. So this is the second objective from this lecture that I expect you to be able to do. Don't really expect you to be able to do this, but I do expect you to know this. I expect you to know where you have horizontal slopes, where you have vertical slopes. But I do expect you to be able to take derivatives implicitly, like I've been doing earlier. And I do expect you to be able to find the tangent line to an implicit curve at a given point. So if we were looking at this example, what you would do at this point is take the derivative of both sides of the equation. This is being done implicitly. Then you would plug in the point. So you're given the point. So this is the x value. This is the y value. You would plug those into all the variables that remain after you take the derivative. Step 2 comes after step 1. You have to take the derivative first, then plug in points. So at that point, the only thing that will remain is dy dx, which you'll solve for. And then once you have dy dx, we know dy dx is the slope. So we know that the slope is dy dx. And you're also given a point. The point in this case is negative 1, 1. So if you have a slope and you have a point, you can use point-slope form to give the correct tangent line. So that's what we're going to do in this example. So we're going to take the derivative of both sides of the curve. So the curve is x squared minus y to the fourth equal derivative of x cubed plus y to the fifth. Okay, so take the derivative of both sides implicitly. You've got the derivative of x squared is 2x. The derivative of y to the fourth is 4y cubed. The derivative of x cubed, oops, almost made a mistake. The derivative of y to the fourth is 4y cubed, but remember, this is implicit differentiation, so you have to multiply by the derivative, which is y prime. On the right-hand side, the derivative of x cubed is 3x squared, and the derivative of y to the fifth is 5y to the fourth times y prime once again. Now, unlike the previous example, where I was going back and looking at finding y prime, solving algebraically for y prime, you don't have to do that here. The reason that you don't have to do that is I only care about the derivative at one point. So if I use the point that I'm given, in this case negative 1, 1, so this is step 1, I've taken the derivative. Step 2, I'm going to take that point and I'm going to plug negative 1, 1 into the derivative, into the equation. Let's say that. Because you're not going to actually plug it in for y prime, because y prime is what you want to solve for, but we are going to plug it into this equation. Let's see, so x is negative 1, y is 1, x is negative 1, and y is 1. All right, let's simplify that. So this is negative 2 minus 4y prime equal 3 plus 5y prime. Now I'm going to solve for y prime. So you've got, let's see, add the 4y over, you've got 9y prime. Subtract the 3 over, you've got negative 5. So negative 5/9 is the derivative y prime, which is the slope. So step 4, you've got a point, negative 1, 1, and you have a slope, which is negative 5/9, which means that our tangent line is y minus 1 equals the slope times x minus negative 1. So y minus 1 equal negative 5/9 x. So you've got three negative signs here, negative, 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 so it's going to be minus 5/9. So y is negative 5/9 x plus 1. So if you add 1 to both sides, the 1 over here is 9/9. So 9/9 minus 5/9 is positive 4/9. So there is the tangent line. Let's check in Desmos and see if we're right. So let's plot that tangent line. The tangent line that we came up with was y equal negative 5/9 times x plus 4/9. And what you'll notice is at the point 1, negative 1, label it real quick. At the point 1, negative 1, the green line here that we found is indeed the tangent line. You can see how it touches the curve at exactly 1 point. Now, it doesn't work anywhere else. It's not the tangent line to any other place on the curve, but it is the tangent line at negative 1, 1. So finding tangent lines at a single point is actually a pretty easy process compared to the previous problem. And this is what I really expect you to know. You need to know how to do this. It's much easier for me to ask this kind of question than it is for me to even ask the first ones we started with, because the first ones we started with, like this one and then this one, there's a fair bit of algebra involved in these. Whereas if you find the tangent line implicitly at a point, then there's not a lot of algebra needed here because you're plugging in the point into the equation. So what that ends up doing is it ends up getting rid of a lot of the algebra. This was pretty simple algebra to do to solve for y prime. So I actually prefer this kind of problem over the stuff that I've done so far in this lecture. This is what I really need you to be able to do on this topic out of section 3.5. All right, there's one last little thing out of section 3.5 that I want to cover, and it is inverse trig functions. You think about all the different derivative formulas that we've discussed so far. We've done logarithms, we've done exponentials, we've done power functions, roots, sine and cosine, tangent, secant, but we haven't touched the derivatives of any of the inverse trig functions. And the reason for that is in order to do inverse trig functions, you really want to do these implicitly. So that's what we're going to do. We're going to look at this implicitly. So if I write y equal secant inverse of x, you should know at this point that if you take the secant of both sides, right, secant and secant inverse are inverse functions, so they cancel each other out. And what you end up getting is that secant of y is equal to x. So the inverse relationship shared by secant and secant inverse are on display here. And I may not know how to take the derivative of the secant inverse, but so in other words, no derivative is known at this point in the course of this original function, but we do know that the derivative of secant is secant tangent. Well, if you don't know, you know now. You may have forgotten, but the derivative of secant is secant tangent. So how does that help us? Well, suppose I take the derivative of secant y equal to x. Then by this derivative formula, the derivative of secant y is secant y tangent y times the inner derivative, the inner function, which is y, its derivative is y prime, equals x, but the derivative of x, I'm going to take the derivative of both sides, the derivative of x is 1. So y prime is 1 divided by secant y times tangent y. And we would love to be able to give an explicit formula for this derivative. We'd love to be able to have it in terms of x, because our original function, right, the original function here is not implicit, it's explicit. So we expect the derivative to be explicit as well. Right now it's not, because y prime is in terms of y, it's not in terms of x. This is where trig can come to our rescue. If we're looking at the function secant inverse, every inverse trig function has what's called a trig substitution triangle associated with it. Secant of y is equal to x. Well, y is the angle, so it would be right here. Secant of y is equal to x. Remember that the secant of any angle is, well, remember it's 1 over cosine, right? And if you've forgotten, cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So what we have in this particular case is we have secant of y is x, but that's supposed to be hypotenuse over adjacent. That means that the hypotenuse is x and the adjacent is 1. Because you need x over 1 to come out of, you need x to come out of that ratio. So if y is the angle, secant of y is hypotenuse over adjacent, the hypotenuse is x, and the adjacent angle is 1. And then we can use our Pythagorean formula to tell us, okay, if I make this thing c, then x squared is equal to c squared plus 1 squared. So x squared minus 1 is c squared, or the square root of x squared minus 1 is c. Now technically this should be plus or minus, and we'll talk about that here in a second. It depends on where your angle is located, right? If your angle is located in the first quadrant, then c will be positive, because your sine value there is positive. If y is located in quadrant 4, then c will be negative. But how does this help us? Well, if you look, I've got y prime equal 1 over secant y times tangent y. It's easy enough to say, okay, I can replace secant y with x, because remember, that's what's happening here. Secant of y is x. But what about tangent y? What can I replace tangent y with? Well, if you recall, tangent of an angle is opposite over adjacent, which for this triangle implies the tangent of y is the opposite side to y, which is c, but c is the square root of x squared minus 1, over the adjacent angle, which is 1. So the tangent here is square root x squared minus 1, depending on, once again, where y is. So this is my derivative formula. This derivative formula is accurate for values of y in quadrants 1 and 2. And then if we had quadrants 3 and 4, we would replace it by the negative term instead. So the point here is there's actually a couple of different formulas that you have for secant, and usually to represent that we involve absolute values. So if you want to see the completed formulas here, these are the completed formulas, and keep in mind the absolute value here is so that we don't have to differentiate between y greater than 0 and y less than 0. In other words, we don't have to care about whether we're in quadrant 1 or 2 or quadrant 3 or 4. So typically, we put the absolute values on the x terms there to compensate for that. So, and there's a lengthier explanation that goes into that. But these are the 6 inverse trig functions and their formulas. Which ones do you need to know? You need to know these 3. these should be memorized, not only for this course, but courses that come after this. In particular, I think the most important one here is inverse tan or arctan. This one pops up a lot. You need to know that formula in particular. All right, I've just basically briefly covered, scratched the surface, so to speak, of section 3.5. What you need to do at this point is go back in and read section 3.5. You need to look at the online notes. So there will be online notes posted. You can look back at this video if you need to. And you also need to work some practice problems. So it's been a while since y'all have been in class, so let me remind you where all that is. If you are on the website, if you go to the home page where we have the outline, we are currently doing implicit and logarithmic differentiation. If you click on that, you'll see here are the implicit derivative notes. Here are some practice problems, so you can click on this for some more examples. These aren't my examples, this is another website, but it's a really good website for y'all to take a look at some more examples in. And then there are some practice problems associated with these. So I just want to make sure that you are aware of those resources. There's also videos. You've got several videos that have different examples from what I just got through doing in this video. So I wanted you to take a look at those and tell me what you think. All right, I hope everyone's doing well. I know this is a stressful time of year for a lot of you with everything that's going on. If you need me, I've got office hours next week. Starting on Monday, take advantage of that. I look forward to seeing you. We can chat. We can kind of figure out what's going on and help each of you. If you have questions, you're always welcome to email me. I'll see you again with another lecture on Wednesday. All right. Thanks. Have a good one.